Hey guys, a little bit of astrophysics, that optional topic. So there's still time to our cram course. We're doing over astrophysics right at the end of that cram course, so roughly about an hour and a half on it. And it's going to be on Monday, remember. So it says here that I've got a crater on Mars. So you're going to imagine you've got planet Mars, you've got some crater on it, and it says we know what the diameter of that crater is. We've got some spacecraft in a flyby. So basically what you've got is some spacecraft, you know it's going to fly by Mars, but it says that it's going to be a distance away when it flies past as 12,500 kilometers. We've got a telescope on that spacecraft, and we're told what the diameter of the telescope is. We're told what wavelength that it observes in. I want to know, can we see this crater? So if you're thinking, when you've got a diameter of telescope, you're either thinking about the power of the telescope or its minimum angular resolution. Okay, so remember the power is proportional to the diameter squared. We're looking at the power, we're looking at the minimum angular resolution. That minimum angular resolution is always going to be whatever the wavelength we're observing at divided by the diameter of our telescope. Okay, and you can double check that equation on your formula sheet, which you should always do because that's from my mind. So hopefully you have your formula sheet open. You're going to go to the astrophysics section, and you're going to go to the part where it talks about that minimum angular resolution. And your formula sheet, it says what it's called the Rayleigh criterion. So that's my Rayleigh criterion, which also means the minimum angular resolution. The wavelength we observe in divided by the diameter is approximately equal to it. Okay, so again, the Rayleigh criterion, or that minimum angular resolution. So what that means is, if I've got 2 points that are really close together, it means can I see them as two separate objects, or if the resolution is not good enough, I might just see it as one big blur. Okay. So what we do is we look at our wavelength, which is our 450 times 10 to the power negative 9, and we're going to divide it by the diameter, which is 0.21, to get that minimum angular resolution. So 450 times 10 to the power negative 9 divided by 0.21 gives me an answer there of 2.14 times 10 to the power of negative 6. So that's what my minimum angular resolution is. So what that means is, let's say we've got 2 points, and again, there's the point that I'm observing from, so like let's say it's my telescope. What we're doing is we're trying to see, can we see those 2 points as two separate points? So what it's trying to tell us is, if the angle is bigger than 2.14 times 10 to the power negative 6, then yes, I can see them as two separate points. So that angle, that minimum angular resolution of my telescope, is 2.14 times 10 to the power of negative 6. Okay? Now, at really large distances, what we can say is basically that center of the triangle is the same as hypotenuse, right? Because at really large distances, again, if we had a small distance, okay, you can see there would be a difference. But at really large distances, there's barely any difference between those two sides of the triangle. So that's why we can say that this size, that center midpoint from where observing to the center of those 2 points, is the same as